Kelly wants to enclose an outdoor rectangular garden where one side of the enclosure is bounded by her house. Okay, so if this is her house over here, she wants to make a garden so that she doesn't have to have fencing for that one side. So it's going to save her money. All right, so she has 90 feet of fencing to work with for the remaining 3 sides of the garden. So let's go ahead and label these X and Y. So X is over here. So there's 2 X's and a Y that add up to 90 feet of fencing. So what we're supposed to do is find the dimensions of the rectangle that will result in a maximum area. So let's find X and Y that will give us a maximum area and then actually find what that maximum area is. Now notice that I actually drew this so it looks like a square. I just didn't know how to orient it. So it could be that it's like this, or it could be like this. I'm not sure yet. So I'm going to put a big question mark here. I'm not sure yet. So that's why I just kind of drew it like it was a square. Anyway, so how do you find area of a rectangle? Base times height, right? Or width times length. So in this case, X times Y. Now we need area just in terms of one variable because I don't know how to deal with taking a derivative with 2 variables yet. That's to come later. Anyway, so to do that, I need to make a substitution for Y. So if I rewrite this perimeter relationship between X and Y, by solving for Y, I end up getting 90 minus 2X. So that's what I can substitute in here. Now, I'm also going to go ahead and distribute that X. Now, this may look familiar. You've probably done this problem in college algebra. The difference is that now we can use calculus. We can take a derivative and find critical values instead of just graphing on the calculator to figure out what that maximum point is. All right, so derivative, 90 minus 4x, set it equal to 0, and you end up getting 90 over 4, or 22.5. Now, right quick, let's throw that on a number line to make sure that that would actually yield a maximum and not a minimum. So I'm going to pick, let's say, 20 and 30 as my test points. So plug 20 into the derivative. When you do that, so remember, derivative, it's right here. When you do that, you'll end up getting a positive number, right? Because it's 90 minus 4 times 20, which is 80. So increasing, so that's good. That's good. So then plug a 30 in, what do you get? So 4 times 30 is 120. 90 minus 120 is certainly a negative, so that's decreasing. Aha! So we do, in fact, get a maximum. So that's just our checking. Okay, so it looks like we have X is 22.5 feet. That's the units, yep, 90 feet. And then Y, you can plug that 22.5 in right here, and you'll get a 45 feet out. So those are the dimensions. So it looks like it's this case, which would make sense because more fencing is being saved by the longer side being along the house. So one thing to note is that this X is perpendicular to the house, and then this Y value of 45 is the one opposite the house. I spelled opposite wrong. Let me try that again. Opposite the house. All right, so those are the dimensions that I was talking about. Now we need to find the maximum area. So the dimensions that yield a maximum area are 22.5 by 45 feet. The actual maximum area, multiply those together because area is X times Y. And what we end up getting is 1,012.5 square